Hello everyone, this is Aisha Tekesh from Kennesaw State University. In this video, I will briefly explain the step response of first-order systems and then how we model Quanser Qube using experimental data and theory altogether. So how do we describe first-order systems? First-order systems are described by first-order differential equations. And then when you take the Laplace transform of the outputs and the inputs, the left side and the right side, and then take the ratio of the output to the input in the Laplace domain, you will find the transfer function as k over tau s plus 1. So this is the most general form of representing first-order systems in their transfer function form. Here k is the DC gain, which will determine the size of steady state response. That means it will be the final value of a unit step response. And tau is the time constant, which determines how quickly the system moves toward the steady state. So if you were able to do experiments in your lab, so you apply a unit step, that means a constant input to the system, and then you will be able to record the data, then you plotted the response, and your response does not show any oscillatory motion. There is no overshoot. That means the system can be represented as a first order system. If this is your case, then we can actually find the unknowns of first order system, which are k and tau. Here k will be the final value, which means like y infinite, which is again your final value. You can directly read it for a unit step response. Again, if this was 2 times of unit step, then it means you have to divide the final value by 2. And its settling time is defined for the system to reach and stay within the 2% of the final value. Let's say your final value is 100, so its 2% will be, or 98% will be 98. So you need to find the time when the system reaches to 98 and then divide it by 4 to be able to calculate tau. Let's do time analysis, step response analysis of first order systems in MATLAB. I use Live Editor because when I run the script, it actually helps me to see the result all in one page, but you're not limited to Live Editor. You can use MATLAB command window or just MATLAB script. So here, I started with some explanation. So here, this is just the text. Here is the transfer function of a first order system, k over tau s plus 1, knowing that k is the DC gain, tau is the time constant. So time constant can be calculated knowing that the settling time. Settling time is the time required for the signal to reach and stay within the 2% of the final value. So knowing this, let's do an example, k being 10, tau is equal to 1. Then we define the transfer function using TF numerator comma denominator. Then I plotted the step response. Remember, k is your final value and tau is the time constant. And if you can read the settling time, if your final value is 10, your settling time will be the time when the system reaches to 9.8. And so we change the k value. Changing the k value changes the final value. So I'm increasing, I'm decreasing it. You will see the effect of k on the system response. But as you see, system does not possess any overshoot or oscillatory motion because first order systems behave like overdamped systems. And then I'm changing the time constant. So if you're looking for a faster response, you need smaller tau values. So I'm reducing the number so you will see the effect of tau on the system response. So the system will quickly reach to its final value, as you see here. I hope this helps. Now, let's collect experimental data, and for that we have Quanser Qube in our lab, and this is the demonstration of how we collect data from system when the input is a step. So Quanser provided all resources, so if you're a faculty, then you should be able to gather all information from the fundamental labs folder. And if you're a student, then it means I already provided you the details and all the necessary files in D12. So you can just go ahead and import everything. So once you open the Simulink model and apply the step input and run the simulation in real time, you will see that on the right screen, the Quanser Qube color, the red color will turn into green. then it means your Quanser cube is connected and is able to, now you will see that the disk is rotating. So you can also adjust the simulation time, and if you double click on the scope, that way you will be able to just see the response. And like it's like a rough analysis. But if you were able to export data in command window, then it means you can do further analysis, which is strongly recommended. Yes, in the previous slide, you see that we were able to collect data by connecting to the Quanser cube and we applied 2 volts. Remember, we didn't apply unit step, but we applied 2 volts. So that means it's 2 times unit step. So your final value should be divided by 2 to calculate K value, which is the DC gain. Here what we do, yes, we collected data, and from here I wrote a simple script, a very simple script to be able to determine the final value, and from here to be able to find the settling time. So if you know the settling time, you can calculate tau. Again, I'm linking it to the theory. And then the next thing, now we know our transfer function. I'm connecting it to the Simulink model. This Simulink model, the previous one was just to collect experimental data, but now I'm using also the transfer function and to be able to validate my model from theory. But you can also use system identification toolbox. Since we have experimental data, we know the input and output. You need to correctly put the initial time, starting time, and also the sampling time. You need to be careful here. Then you click on estimate to fit a first order system transfer function. You can export that into the command window. With that, you will be able to get all details about the fitted transfer function. So you're really looking here for high fit, like 95%, 96% fit. And you can now include the second transfer function from the system identification to be able to compare the experimental data, transfer function from theory, and transfer function from system identification.